continuing with our investigations of the bundle adjustment problem, or the problem of multi-view reconstruction. Before we look into the numerics of the bundle adjustment problem, that is the question, how can we actually simplify our problem in order to solve it in a practical way, I just give a, let's say, 5-minute repetition of what the bundle adjustment problem was and why this is a very relevant problem in photogrammetry. So the problem that we are addressing, or where bundle adjustment came from, was we have a number of images, and originally these were images taken from an airplane of the surface of the Earth, and the task is to estimate a geometric model of what is observed in the images. That means there are distinct points, traditionally selected by a manual operator, but in modern systems typically done with automatic feature extraction, identifying points, the same point in multiple images, and then the task is to estimate the coordinates of the individual points in the environment, for example, those points over here, as well as the locations of the cameras from which those images have been taken. And we may additionally take into account information about control points. These are these triangles over here. That means points for which we know the 3D location in the world, and we want to compute the coordinates for all those points and the orientation parameters for all those cameras, and potentially also the intrinsic parameters of our cameras, all at the same point in time. And the bundle adjustment solution tries to solve this problem through a least squares problem, and it basically, this kind of the key equation of the problem is we have the coordinates of our observed points. So this is a 2D point observed in some arbitrary frame in our camera, can be calibrated, doesn't have to be calibrated. And what this ij means, we observe the point I in our image j. And then we have our corrections in the same frame, and this should be equal to a scale factor because we're operating in homogeneous coordinates, and then the projection matrix of our camera, and we have our and these. So the question is, why does this projection matrix depend on the individual points? This is the case, or we may need to take into account the coordinates of the point in our image plane if we have nonlinear distortions. So we potentially want to consider also nonlinear distortions, for example, from the lens, like something like a barrel distortion, for example. And we have our camera parameters in here and our non-parameters in here. And additionally, we have the 3D point in the environment. In addition to that, we have an uncertainty with which we can actually measure these individual points in our images. We have that for all points, for all images. And the goal is now to find the 3D location of those points and to find the camera parameters, that means the intrinsics and the extrinsics, in order to reconstruct the scene of the environment and in order to know where the individual cameras have been taken. And so this equation encodes once the projection from the 3D world to the 2D world. So we are here in the 3D world and map it to the 2D world, and this projection happens in this projection matrix. And in addition, it also encodes the collinearity constraint of those points. That means that we have this idea that this is the point I, and we can see this point I over multiple images. And this makes the connection that we actually observe a point in 2 different camera images, make an observation of the same point in the environment. And this data association problem, which point this is already encoded in this equation due to the indices I and j. And we assume this to be correct. So we assume to know if we observe a point in our image, we can actually associate that with a real 3D point in the environment. So we have a quite large number of unknowns involved in here. Every point, a new point means not a known control point. xi has typically 3 coordinates. Then we have our scaling parameter, and this is the scaling parameter is a result that we operate in homogeneous coordinates. Then we have our projection matrix, which depends on the 6 exterior parameters, the 5 intrinsics for the linear case, and potentially some parameters for the nonlinear corrections. So, and we did one trick in order to get rid of the scaling parameter. We actually went back to the Euclidean world, because then we can eliminate the scaling parameter and dramatically reduce the number of unknowns that are involved. Once we have done that, we can proceed with the kind of standard procedure. We have a couple of unknowns, we have a couple of observations, set up a system of linear equations and solve this system of linear equations and come up with a solution for the coordinates of the points and the orientation of the parameters. So this is more or less where we ended up last time. And the question was now, can we really do that? So can we take this kind of standard procedure and actually use it to solve practical problems in the context of finding the orientations of our cameras and estimating the location of the points in the environment? And the claim that we said that we cannot solve that in a straightforward manner. And the main problem that we have is that the number of unknowns and number of observations are both very large. And if you build up a standard system of linear equations, we actually come up with a very large system, and we can typically not solve this in a reasonable amount of time. So we had the examples. So consider we have 20,000 images. We see 18 points per images, and on average we see every point 3 times. So this ends up that we will see 20,000 times 18 divided by 3, because we see every point on average 3 times. So 20,000 times 6. So 120,000 points. Every point has an x, y, and z coordinates. So we have 360,000 location parameters for the points in the environment. And as we have 20,000 images, and assuming we have a calibrated system, then we have 120,000 orientation parameters, which is the x, y, and z position, and the 3 rotational components for every camera. So in sum, if we just sum those values up, we have 480,000 unknowns and around 720,000 observations. And if you just set up our coefficient matrix, it will have approximately 3.5 to the power of 11 elements. And if we compute the normal equations, 2.3 to the power of 11 elements. And this is a quite large number of elements if you want to solve this system of linear equations. And therefore, we typically need to apply some tricks in order to solve these problems in an efficient manner. And what I'm trying to explain you today is how we can actually do that. In order to kind of understand that problem a bit better, we look to a concrete example. So we have a small example. So consider this was an airplane flying approximately on this trajectory through the environment and recording a couple of images. So we have a set of 7 by 7 points over here. So we have 3 stripes, and every of these stripes consists of 7 images. So we have 21 images, 7 taken over here, 7 taken over here, 7 taken over here, and we have 49 points in a 7 by 7 grid, and 4 of those points, so 1, 7, 43, and 49 are known control points. So 4 full control points, that means we know their x, y, and z location. And we have a certain overlap between those images. So in this direction, we have 60% overlap of image 1 to image 2, and kind of those in the second stripe, they have an overlap of approximately 20%. So we can see here always the point on top from the previous row, and one of the points that will be seen in the next row. And so what we want to do is now we want to estimate how does this the coefficient matrix actually look like, and can we actually maybe do a trick in order to solve this problem in a more efficient manner. Okay, so we said we have, if you look at our problem, we have 6 images which only see 6 points over here. So this was kind of the first image, sees only these points. The same holds for this image, and so always the ends of the rows. Then we see only 6 points, and in all other images we see all 9 points. So for example, image number 2 will see 1, 2, 3, 8, 9, 10, 15, 16, 17. So we'll see 9 images. So if we have all those observations where we have 15 images with 9 points, 6 images with 6 points, and so this ends up in 171 image points, and every image point has an x and y coordinate. So we have in sum 342 observations. So individual coordinates, x or y coordinates that we are going to observe. And in addition to that, we have a number of unknowns, and the number of unknowns are the number of points that we have, minus the control points, times 3, because every point has 3 degrees, an x, y, and z coordinate. So this is 45, which is 49 minus 4, times 3 gives me 135 unknowns for the location of those points. So these are these individual points. And as we have 21 images with 6 unknowns, we have 126 unknowns here for this problem. So in sum, we have 261 unknowns and 342 of the individual observations. We will now, so keep this structure in mind. We are flying here, observing image 1 to 7, then the second row, and then the third row. And there will always be overlaps that in every image I see points that I've seen in the previous row and points that I see in the next row. And there's also an overlap between consecutive images, which I can observe. And now I want to look into this coefficient matrix and actually change this coefficient matrix, or not change, but discuss a structure or a smart structure of this coefficient matrix in order to solve this problem in an efficient manner. So the first thing that we do, if we would maybe start intuitively, we would say, okay, so how does our parameter vector looks like? We first have the first 6 parameters for our camera. So the x, y, and z coordinate for the projection center, and then the 3 rotational components. And then I see the first 6 points, so I add xy of point 1, xy coordinate of point 2, xy coordinate of point 3, and so on and so forth. Then at some point in time I take the second image, so I add the x, y, z yaw pitch roll of the second image, and then kind of continue adding the new points to my state vector. That's one way I could do that. So I propose a slightly different way. And this is, we split up our vector of unknowns into 2 vectors. One are the 3D point coordinates of our points. And then the second part of the vector consists of the orientation parameters of my camera. I'm basically just sorting my vector of unknowns. So that first I have a block which are just x, y, z coordinates of point 1, x, y, z coordinate of point 2, x, y, z coordinate of point 3, and so on and so forth, until all points that I've seen up to now are stacked together. And then comes 6 parameters for the orientation of the first camera, 6 parameters for the orientation of the second camera, and so on and so forth. So it's just a reordering. Okay, if I have this reordering, that I have k always the point coordinates and t are the orientation parameters, I can also split up my matrix A into 2 parts, consisting of 2 matrices, a matrix C and a matrix B. And the matrix C basically is everything, it contains everything which has to do with the 3D point coordinates over here. And the matrix B encodes everything that relates the 6D orientation parameters of our cameras with our observation space. It's just, this happens only based on reordering. And then, if the matrix A has this form, I can actually write this as C times K plus B times delta T. So nothing very bad has happened. It's just a reordering so far of all variables. Okay? Is that kind of clear that we can do that just by reordering our variables? Okay, good. So the next thing we can do, then we can say, okay, we had our delta L plus the corrections is A times delta X, which then has this form. And then I can now look into every individual observation. So the observation of one point in one image. So this is Lij, point I in image J. So this can write this as Aij times delta x. And this is 2 times u-dimensional. So u are our unknowns. I think that's maybe sometimes called n, sometimes is u. So this is the number of unknowns that I have. And now the key inside sits actually in this equal sign over here. So this is kind of the important thing. And this says an observation of one point in one image will only depend on the coordinate of this point in the 3D world and the orientation parameter of the camera. It doesn't depend on the orientation parameter of any other camera or on the 3D coordinate of any other point. So if I observe point I, it doesn't matter where point I plus 1 is for this equation. So that means the only elements that matter in this equation is a 2 by 3 matrix, because so we're mapping in the 2D space of our observations of the xy coordinate, and we have a 3D location of my point I in the space, and here a 2 by 6 matrix mapping from our fixed orientation parameters of my camera into the observation space. I just have these two elements which matter. So the thing is, so this is actually one of those elements in A here, one of those rows. And this row can actually be, so this row times delta x can actually be expressed by this expression where only a 2 by 3 matrix and a 2 by 6 matrix matters. Okay? So this whole row over here. So this row multiplied with this vector delta x, only those elements matter. And the insight is that, again, if I observe from this camera location a point over there, only the location of the point and the camera position actually matters for this observation. It doesn't matter where another point is in the world or where the camera in the next point in time looks to. Okay? So this means if we look to these individual elements over here and when we write them as long rows, given that the delta x vector is not a zero vector, this implies that I have a lot of elements which are 0. So I have a 2 by 3 block. Again, a lot of elements which are 0. This is kind of the part which splits the delta k, so the coordinates of the points in the 3D world, and the orientation parameters. We have again a couple of zeros, then this bij, which is 2 by 6 matrix, and again zeros. So these are kind of all camera parameters for the camera with the index smaller than j, so from 1 to j minus 1, and from j plus 1 to the number of images that I have. And those zeros here correspond to all points which are not the point I. So these are all the points from point 1 to I minus 1 and I plus 1 to the number of points that I have. They are all 0, and only those blocks are non-zero, because these are the blocks which again encode the location of the point and the orientation of the camera. So what is the mapping between the 3D coordinates of the point and the orientation of my camera, how this maps into the space of observations. And only those two parts matter. The coordinates of the other points do not matter for computing this observation. So what follows from such a structure? If A has this form, this Aij, what does this structure imply? So I do this for the first observation, second, third, fourth, fifth, and so on. It means that this matrix, the matrix A, in the end consists mainly of 0 elements. And they're just a very small number of small blocks, small compared to the overall size of the matrix, which are non-zero. So if we go back to our initial assumption, we said, computed something, whatever, we had 3.5 to the power of times 10 to the power of 11 elements. this is true. We have so many elements, but most of those elements are actually 0. Yes?
I have one question. This assumes that all the points are uncorrelated with each other. Is it also true when it is, for example, 9 points of one image?
So we are not looking in this stochastic model. We're looking to the dependency. So given I have the coordinates of those points, so the coordinate of the 3D point and my camera, what is the observation that I should obtain? So we're not taking any statistical model here into account, just a functional dependency here at that point. Okay. So we are not modeling the probability distribution here at that point. So it's the mapping from the space of unknowns, which are the orientation parameters, into the observation space, into the space of observations. So at the result, we have a sparse matrix. And the sparse matrix mainly has 0 elements. And this is one of the key things I can actually exploit when I need to do my computation. So I should use sparse matrices, the first important take-home message here. But as you can see, we can actually do more than that. But let's first look into the sparsity pattern. And the nice thing is if we sort our vectors in the coordinates of the 3D points and the orientation parameters of the camera, the matrix A actually gets a nice interpretation of what's going on. We can actually draw this matrix over here. So this is our matrix A, consisting of an element C and an element B, which consists of these Bij's and Cij elements. So what we have here, we have the number of observations. The observations are 2-dimensional. This is, of course, for every point, a kind of 2x2 block, so that we 2 times the number of observed points, the general number of observations. And here, I have this length is the number of points that I have times the dimensionality of the point, and the number of images or image orientations that I have times 6 because of 6 parameters. So this is the structure of the matrix. And then I have a couple of blocks over here. These are all kind of small 2x2 blocks because it says how is the x-coordinate. So the x-coordinate of a point connects us with my observation, and this thing here connects the orientation parameters with the corresponding observation. So if I basically draw a line down here through this matrix, if I count the element along these lines, it's the number of times a point actually gets observed. So if I kind of count the non-zero elements, and I'm considering now, if I say number of times, I mean kind of 2x2 blocks in here. So kind of 1, 2, 3, 4, 5, 6. So this point over here gets observed 6 times in my data set. These are the number of observations that I have, and I have here 6 2x2 blocks of 6 observations of this point. Okay? I can also do the same thing in here. This is ordered according to the observations and my images and observations. This block basically tells me the number of observations I have for every image. So these are the images, and so if I'm in image whatever 1, 2, 3, 4, 5, 6, image number 6, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9 probably. So I see 9 points in my image. So therefore, some of the blocks are larger, some of the blocks are smaller. The blocks which are larger correspond to those images where I see 9 points, and the blocks which are smaller corresponds to those elements where I see only 6 blocks. There may be points which are even smaller. This one over here is only 5, just because I'm not considering the control points in here. So the first point was a control point, so this should be even only 5 elements in here. Okay? So this is kind of an important observation. So if I see such a structure, I can already tell something about from which image I have observed which points. Have I returned to a position where I have before? So if I would fly the same route a second time with my airplane, this matrix would of course expand down here, and I would see a similar observation pattern down here. And you can say, okay, these observations over here and these observations over here are actually observations of the same area. So the points have been reobserved. Something that I can, for example, see. Okay? So any questions about this structure over here? Okay. So just basically to summarize what I've said before. So if you look about...
Just one question.
Yeah, sure.
I mean, you created these matrices now, which are, of course, easier to calculate. However, the dimension of the matrix has not really shrunk yet. The dimensions are still the same.
So the dimension of the matrix is still the same. So if I would use a standard matrix class for doing my computation, which stores all elements of this matrix, I would have the same problem that I do a lot of multiplications, for example, with 0 elements, they are all 0. Yeah. The thing is, what we typically use in this setting is actually a smarter implementation of a matrix, which is a sparse matrix. And what these sparse matrices do, they basically store only those points which are non-zero. They don't store the 0 elements. And so once you have those sparse matrix implementations, actually every matrix library today supports those sparse matrices, then all the computations don't have to iterate over all these 0 elements. They only access those elements which are non-zero, and then the computations are dramatically faster. So it's basically, so the thing of exploiting these sparse structure is something which comes automatically to you if you use a sparse matrix library. And then there are also variants of sparse Cholesky factorization, for example, which explicitly takes the sparsity into account and is dramatically faster than doing this with a dense matrix.
So the benefits do not come from the mathematics, but from the implementation?
In a sense that you're basically exploiting the fact that a multiplication with an element which is 0 leads to 0, and then you don't have to do this calculation. Yeah. And the thing is, of course, so for you as a user, you don't have to do a lot of things except of saying, oh, this is not a matrix, this is a sparse matrix. And then you can use all your standard computations as well. This is true, and also kind of the math behind those sparse matrices is slightly different because you don't iterate over all the individual elements, which are 0. You use a smarter way for example, multiplying or inverting your matrices, which explicitly exploits those sparsity patterns. But that's something which is from modern, or most of the matrix libraries completely encapsulate that for you. So the first thing is you need to know that you can exploit those sparse matrices, because if your matrix would be densely populated, there's no gain, actually. Then it's actually suboptimal to use a sparse matrix. But we can do more. So this is kind of one of the things which leads to a key improvement in terms of computational speed are these sparse matrices, but we can actually do more, as we will see in a few minutes. Okay, so again, about the matrix C, so this block of my matrix A. Again, this only consists of the submatrices, and these submatrices, what they do, theseCij's here, is to connect an observed point in my image with a point in the real world. So a non-zero element means that I have an observation of a point, and this specific observed points correspond to this point in reality. And there's only one 0 block per row. So in every row of C, there's just one of those 2x3 blocks. Therefore, I put kind of, it's not the exact row, it's kind of the row which fits this block pattern. Okay? You can do a very similar thing for the matrix B. The matrix B consists of blocks of 2 times 6 matrices, and they connect the image point, so the individual observation, these have been the observations over here, or here, with an individual image in the sense that every image has one 6-dimensional vector for the orientation parameters. So it connects an individual observation with the orientation parameters of the corresponding images. And again, for every row in A, I have exactly one non-zero block. Okay? Because an observation, one specific observation, always belongs to one image and therefore to one coordinate of the projection center of the camera and a 3D rotational component. One observation sits in one image, it doesn't live in multiple images. Therefore, I have just one element per row over here.
So this means that one row in rotation marks means 2 rows?
Yes, if it's a 2x6 matrix, yes, exactly. So, so all the names here in terms of rows are always in these blocks of 2 by 6 in B and 2 by 3 in C. Okay? Okay, then we actually need to compute those matrices B and C. The nice thing is we have done that already. So in Photogrammetry 1, in the projective 3-point algorithm or spatial resectioning algorithm, at that point in time, Susanne presented the least square solution and computed the individual elements of these matrices, and just a copy-paste from the lecture from the previous year. So we can directly exploit this. So what is the impact of the mapping of observing a point in my world into my space of observation. So from the coordinates into the space of observations. And these are just the individual element depending on the coordinates of the points that I'm observing. Camera constant sits in here, and different parameters that performs this mapping. We have this for the B and for the C. So every of these individual blocks here, so all the non-zero blocks, are actually exactly those matrices over here. Computed, of course, 4 different points, 4 different observations in different images, but these are the kind of parameter which sits here in this model, assuming that everything is calibrated in here. So these are the equations for the calibrated camera. Okay, so what would be the next step? So we have our matrix A, and then we would build our normal equation. So we have our matrix A, and then have A transposed times uncertainty of the observation inverted times A, and this leads us to our matrix N. So this matrix, so given that this matrix is sparse, this matrix is typically also sparse. But it is somewhat denser, so slightly more densified. But we still have an interesting pattern over here. So we have this part over here with which is the part which only belongs to the 3D coordinates of our points. So these are 3 by 3 block matrices over here now. So X, Y, Z corresponding to the X, Y, Z location of every point. So first point, second point, third point, and so on. And all the rest remaining part is 0. And down here we have the orientation parameters of the individual camera images that we have taken. And then we have in the off-diagonal blocks, so this block over here and this block over here, tells me what is the relation between those elements. So for example, that this image point over here has been observed in those images over here. This is basically what those entries tell me. So this matrix directly tells me what is the connection between this point over here and where it has been observed. And this is given through those elements. So this image point is correlated with this camera position, and with the next one, and with the next one. And then with one down here, with this one, and with this one, and with this one. Okay? This is the information that I obtained from this matrix. So from this matrix, I can directly read how the individual variables are correlated with each other. So it actually, one connection is slightly off topic now, but what we can also do if we have such a matrix, we can also use it as a description of a graph structure, where I have individual elements, individual nodes, kind of just draw them in the same geometry as it is drawn here, and this corresponds to point 1, point 2, point 3, the variables of the point 3. And then we have our camera poses. So this was, okay, pose 1, pose 2, pose 3. And then actually those connections, so those non-zero elements over here, actually tell me that there's a connection between those points. For example, as an example like this. And so this can be seen as a representation of a graph which relates individual random variables with edges in this graph. And these edges model a dependency. And depending on the values over here, how far they are away from non-zero, the stronger the dependency between them. So there's one way of seeing an information matrix in this form, and there are several approaches which are actually motivated from the fact of using this as a graph or even going one step further, is a probabilistic graphical model. So there's kind of a strong connection, or it's actually an equivalence between the bundle adjustment problem and a lot of approaches which use graphical models to represent those facts. And the connection comes actually from this matrix. So the key thing is we have here our 3x3 block elements telling me something about the individual, or the information I have about the individual coordinates of points. The 6x6 blocks, which tell me something about the information I have about the orientation parameters of every image. And I have, from my observations, the links between the individual points and the orientation parameters of my camera. Okay? Okay, so we have the same example, but just for a larger set of images. So I have now 7 stripes with 15 images per stripe, not 3 stripes with 7 images. So it's kind of this problem made larger. You can actually see there again much more zero elements than non-zero elements. And the same holds also for our matrix N. So the number of non-zero elements compared to the overall number of elements in this matrix gets smaller and smaller and smaller. This becomes clear because there's a linear relationship between the number of points. So typically I have a constant number of points I observe in every image. So if I add new images, I just add a constant number of points. So the number of non-zero elements I have grows linearly with the number of elements that I add, but given that the matrix is quadratic, the growth of non-zero elements is quadratic. So the number of non-zero elements grows much faster than the number of zero elements grows much faster than the number of non-zero elements. So I have a quadratic number of elements, and whenever I add a new row, I just have a constant number of non-zero elements that I add. So I have a linear increase in the number of observations that I add. But the number of overall elements I have in the matrix goes quadratically. So the larger my problem gets, the sparser it actually gets, which is great. So if I add more images, map a larger region, see more new points, the relation between non-zero and zero elements is always towards my advantage. So it gets always sparser and sparser and sparser. Okay? So you see here, the first problem we had in our matrix A, around a bit more than 3% of the elements non-zero, and around 10% in the matrix N. If I have a larger problem with not only 3 stripes, but 7 stripes, these values drop always and get closer and closer and closer to 0. Okay? So if I'm just looking into this matrix N, can you imagine a situation where I take more and more and more and more data and N doesn't get sparser? Yeah?
If all points are seen from multiple images, the more images observe one point.
Exactly.
The less far.
So even a step further, if I have a number of points in a scene, and the points are seen basically from every camera image. So I have, let's say I have the image, the points here on my desk, and I have a camera moving the camera around, always in the same area, and they're always observing everything. Then this matrix N will get densely populated. But as soon as I have large scenes where I not always observe exactly the same area, but expand the area and have visibility constraints that I don't see every point from every image, those matrices are really sparse. Okay? Okay, so I think we'll make a 5-minute break, and then we are going to continue here and see how we can actually optimize this matrix N in order to make our life easier and our computations faster. Thank you.